photons in large momentum transfer processes. As I go throughout the talk, you'll find that I've made some notations concerning things that are in an appendix. And there are quite a few transparencies that I've put there that will give you some hints or aids in working out some of the results that I'll be showing you here. For those of you that are following along on laptops, please be warned that, as is usually the case, this particular set of transparencies has been undergoing a state of evolution, and I've added a few things here that are not on the web. As soon as the webmaster back in the U.S. that handles our website gets the copies I send him, he'll update it. So they will be updated shortly. So this afternoon I want to talk a little bit about why photons are interesting, why people use them in high PT processes, give you some history, talk a little bit about direct photon production, the reversed process where we talk about jet photoproduction, where photons in the initial state, talk about some theoretical improvements beyond simple next to leading order calculations, in particular the application of various summation techniques, and show you some of the effects when applied to data and some conclusions. Well, why photons? It's pretty obvious. It's a well understood electromagnetic interaction. We can use photons as a well-defined probe of strong interaction dynamics. After all, that's what we've been talking about so far through deep inelastic scattering, lepton pair production, and you'll hear more about E plus and minus goes to hadrons. Well, you heard about it in the last talk. So, direct photons, photoproduction, two-photon processes, which I won't talk about this time, but which are nevertheless important, all make use of this fact. And furthermore, calculations for the proposed ILC are going to rely on a detailed understanding of how to treat photons, because as we'll see, photons are not as simple as you might have thought. Okay, so what's some early history? You have to really go back to the time of the ISR in the late 70s, the early 80s, and fixed target experiments, the ISR, which was a proton-proton machine, all were running prior to the P-bar-P colliders. And the point is that at the energies that were then available, jet identification was both difficult and controversial. People had seen jets in E plus and minus annihilations, but in a hadronic environment it proved extraordinarily difficult to observe jets, and it really wasn't conclusively done until one reached very high transverse momentum at the ISR, and ultimately, of course, at the P-bar-P colliders. It may be hard to imagine, but in the 70s, the QCD hard scattering formalism that you're learning about here was not fully confirmed. And you had competition from other models, in particular the constituent interchange model, which today would be called a higher twist type of calculation, some of which were mentioned in Sarah's talk yesterday. In particular, the ratio of photons to pions produced at high PT came out quite differently in QCD versus this CIM, and it was proposed as an early test of QCD. As was the observation of the QCD Compton process, which is just another term for quark-gluon scattering to give you photon quark, which was proposed as a test of QCD. As I say, it's hard to imagine that there was a time when we were testing QCD as opposed to today when we simply use it as a tool to understand high energy interactions. But as we went on through the 80s and into the 90s, there was certainly a greater reach in transverse momentum. The P-bar-P colliders came along. Jet production and detection became relatively routine, modulo the comments you've heard about jet definitions and agreements on them. The QCD hard scattering expectations were completely confirmed. The event structure that one expected with two jets roughly balancing the PT was observed. The dijet angular distribution was confirmed, and basically the QCD expectations for direct photons were also confirmed. but you'll see there are some exceptions to that statement, and that's really what we're going to be talking about today. So the focus shifted from testing QCD to using QCD as we do today, and as Wookie mentioned in his talk this morning, the QCD Compton process involves an initial state gluon, so there was a lot of effort put into direct photons because it was felt that this would be a reliable probe of the gluon distribution, particularly in proton-proton scattering where that process would dominate. All right, so today, probably many of you have seen talks on direct photon production. You may have seen this particular transparency. And this comes from, there are some reviews, I've cited one of them here. There's an online database that's maintained in Durham. Let's talk a little bit about the structure of this plot. What's shown here is the ratio of data over theory. So ideally, if everything was well understood, all the data points would line up on 1 with theory agreeing with the data. And what you notice is that there's some significant scatter as a function of this variable xt. Xt is 2pt over root s. And as you'll see later, it gives you a measure of the value of the parton momentum fraction that's being probed by a specific process. So you look at this and you say, well, that's not so good. We've got data over theory that's ranging from 1 down to 1/2 and up to something on the order of 3 or 4. What's going on? Do we really understand direct photon production? And some people have suggested that there's something wrong with direct photon theory. I don't like that particular phrase, because after all, direct photon theory is QCD with a little bit of electromagnetism thrown in. Okay, so what I want to do today is sort of take apart those predictions, because as it turns out, the inclusive cross-section PT distribution is just one piece of information that you can get. You can look at other types of differential distributions and learn a lot more about what's going on. As you've seen already in this school, the event structure is going to depend on a number of things. And in particular, what we can do is ask, where are the photons produced? That is, how are they correlated with the jets and other particles in the event? What's the energy dependence of the cross-section? What's the absolute cross-section? All of these go beyond just the measurement of the PT distribution. Now, for each of these questions, in order to answer it, what you have to do is take a look at the parton level sub-processes that are involved. And one ideally would like to actually learn about the hard scattering itself, and we can do that. I'm going to show you some ways to do that. So first, what I want to do is review some theoretical ingredients, and then compare theory and data using observables that go beyond just the PT distribution. Look at ones that directly test the underlying production mechanism. We'll look at, for example, photon jet mass distribution, angular distributions, correlations with other hadrons. And I'll also draw some comparisons with jet photoproduction, which, after all, has a photon participating in the hard scattering, but in a different way. It's in the initial state rather than in the final state. And also, along the way, we're going to take a look at other examples of single particle inclusive production in pions and see what we can learn comparing production of photons with pions. Okay, so lowest order, simple picture. Here we have direct photon production. There are two to two processes. The Compton process, quark gluon to photon quark. That's a Compton. That should be a quark. And QQ bar goes into photon gluon. The basic picture that we'll use is the same parton picture that Wookie talked about this morning. We'll have a couple of partons photon distributions will integrate over dxa and dxb, the two momentum fractions. The PDFs will have scale dependence. We'll have a squared matrix element, flux factor, and phase space that we'll be integrating with. Some of the details concerning variables, floor vectors, other kinematic definitions, and so on are referred to in the appendix. And also there's information to be found on our website in the Handbook of Perturbative QCD. So I'm going to assume that we can go ahead and do these lowest order calculations. And ask now what would happen if you were to do a next to leading order calculation, that is looking at all possible order alpha, alpha S squared subprocesses. Well, the first thing you need to do is you draw all possible one-loop virtual contributions, all the corrections to the 2-to-2 processes. Then you pick up quark-antiquark annihilation into a photon and two gluons. Here's the Compton process with an extra gluon in it. And there'd be some other new processes that don't have counterparts in the lowest order. In this case, it's quark-quark scattering with an extra photon being radiated. Now, I should point out that for the two lowest order processes, there's a simple event structure that you would expect. That is, a photon appearing by itself at high PT on one side of the event with a jet coming from a quark or a gluon on the opposite side of the event. So the photon would be well isolated from other produced hadrons. But now let's look at quark-quark scattering with the production of an extra photon. So this blob here can refer to other processes in addition to just quark-quark scattering. What I'm really focusing on is something very similar to what Carlo did in the last lecture, namely what happens when you have this extra leg right here where the photon is radiated. So I'm not really concerned about what's going on here. This process will factorize. Once I square the amplitude, it's exactly the same type of thing that Carlo went through. And you'll find that you'll have the squared matrix element for quark-quark scattering here. And then you'll pick up a term which describes this vertex where quark radiates a photon. And it has a structure which in this case looks like an ultra-Parisi splitting function, but it's one that involves a photon. So it's P gamma Q. It's actually proportional to the splitting function for a gluon coming from a quark, but with obviously a different coupling. Now we've got alpha here, not alpha strong. And the color factor will be different. Now, if we have a massless quark in this final state here, when we radiate the massless photon, we'll have a collinear singularity, which will have to be factorized in the same manner that Wookie talked about in factorization theorem this morning. That singularity is factorized and absorbed into what's called a photon fragmentation function. And that photon fragmentation function has both a perturbative piece and a non-perturbative piece to it. And this gets us into an aspect of photons which may be surprising at first sight. Most people think of the photon as just interacting as a point-like manner with charged particles, either electrons, positrons, muons, or quarks. But in point of fact, the photon can interact hadronically as well. There's a model, an old model, called the vector dominance model, in which the photon undergoes fluctuations into rho mesons, omega, phi mesons, which of course do couple hadronically to other hadrons. That gives you actually not a bad description of the photon-proton total cross-section behavior if you start with the pion-proton cross-section. The point is that there is a hadronic aspect to the photon interactions with quarks. So we have actually a set of equations that are the usual Altorelli-Parisi equations with one new term in it. And that's this piece right here that involves the photon splitting. And so now we can calculate the Q-squared dependence of a quark fragmenting to a photon or a gluon has the same structure as this piece right here, with the alpha S in it. It has the same structure as for, say, planned fragmentation functions. But there's this inhomogeneous term that sits out here with no alpha strong. That has a very interesting consequence. Now, as with any of the Alter-Parisi equations, we can calculate the Q-square dependence of these fragmentation functions, but we can't calculate the boundary value. So you have to have some model that tells you what these fragmentations start out as, but once you know that, you can calculate the evolution in Q-square. There is one additional proviso, and this is worked out in detail in the appendix, and we'll refer to this in several points. If you actually solve this set of equations, and the solutions given in the appendix, what you'll find is that the quark fragmentation function is proportional to this term here. In lowest order, in higher order, it modifies the z dependence, but the important point is that the leading term is calculable by solving these equations without knowing what the boundary conditions are. And the leading behavior of this fragmentation function is that it rises linearly with log of q squared, which is quite different from the normal hadronic fragmentation function. Okay, so we put this fragmentation component in, and clearly the situation becomes more complicated. In lowest order, you expected to see a photon produced all by itself, in isolation, recoiling against a jet. But now we expect to see a fragmentation, or sometimes referred to as a bremsstrahlung component. And there, the photon is going to be a fragment of the jet. So they're going to be hadronic fragments accompanying the photon. It won't be as isolated as you might have thought had you only stopped at the lowest order diagrams. And of course, we'll still have some fraction of the events where you have no hadrons accompanying the photon. This first one, the direct or point-like part, is going to dominate at high energies because basically you don't want to waste any energy producing extra fragments that go along with the photon. If you want a photon at high transverse momentum, you want to give as much of the subprocess energy to it as possible. But, as I mentioned, the fragmentation function has this rather unique behavior that is going to be proportional to alpha times log of q squared. That's alpha electromagnetic, which looks basically like alpha over alpha s. So if you're counting powers of logarithms or powers of alpha strong, it turns out that you get the same power as you would with the lowest order terms if you convolute your basic 2-to-2 quark or gluon term with the appropriate photon fragmentation function. That'll give you the same power of alpha strong as the lowest order would. Likewise, you can have a convolution of 2-to-3 scattering with an appropriate photon fragmentation function. That will give you something of order alpha strong squared. So now, it appears that we should be including this fragmentation component even in lowest order. Okay, a couple of comments here. So we can produce the photons as fragments of jets. The jets are produced by all the usual subprocesses that we'd be thinking of. So therefore, the production of photons is every bit as complicated as the production of jets, with some additional terms thrown in. So the original thought that somehow studying photon production was going to be a simple test of QCD and proton scattering, the Compton process would dominate, it would be very straightforward, turns out not to be true. Turns out that anytime you have photons, you're going to have all of the same subprocesses that you would with hadrons, and then you'll have a few extras. So photons turn out to be more complicated, not less. Okay, a couple of comments on next to leading order calculations. You saw nicely illustrated in the last lecture the fact that once you go to 2 to 3 processes, you're going to involve collinear singularities. soft singularities. You're going to have to treat them in some manner. Usually we use dimensional regularization these days. And you're going to have to factorize singularities, absorb them into either the fragmentation functions or the distribution functions. There's a lot of stuff to keep track of in order to be able to generate finite, reliable predictions. Well, there are a couple of ways that this is done. If you're looking at something like an inclusive cross-section, you want a PT distribution, it's possible to do the phase-space integration symbolically, get an answer once and for all that can be coded into an appropriate subroutine, and then you can do the integrations over the momentum fractions numerically. That's suitable for distributions that are not very differential, so like a single PT distribution. On the other hand, if you're interested in correlations between, say, the photon and the jet, or you want to place cuts, experimental cuts on a photon and some of the accompanying hadrons, you might want to have access to the 4 vectors for more of the partons in the final state. And in that case, you might want to do all of the integrations by Monte Carlo. But of course you have a problem. There are singularities there, and you have to arrange that the singularities are going to cancel each other so that you end up with finite answers. And there are 2 basic ways that people use. One is the phase-space slicing method, the other is the subtraction method. I have included in the appendix some references for the phase-space slicing as well as an example as to how it's actually used. The end result is it's a bookkeeping technique that allows you to ensure that the predictions that you make are actually finite, that all of the singularities have been appropriately factorized. Okay, so suppose you're armed with the techniques to go ahead and generate some predictions. You want to look at some data. And the question is, what data should you look at? What variables are important? What variables will tell you something about what's going on in the hard scattering? So I've included a few here, some of which you've seen before. For example, the photon jet invariant mass. Well, this is very similar to the dilepton mass that was discussed yesterday by Sarah. In this case, m squared will be just the product of the 2 x's times s. So if you're looking at, this is lowest order kinematics, so I'm thinking of the final state as a photon and a jet. Its mass is just the partonic center of mass energy, so that's why you have this expression. The photon jet rapidity would just be given by the average of the rapidities of the photon and the jet, whereas the difference of the 2 rapidities can be related to the center of mass scattering angle. That's a very convenient expression because, of course, the rapidity difference here is going to be invariant to boosts along the beam direction. So you can use the overall hadron center of mass at a hadron collider, for example. You can use rapidity measured in that frame to actually determine something about the center of mass scattering angle in the parton frame. Now, if you put all of these together, and some of this kinematics is worked out for you in the appendix, you can figure out that at lowest order, XA and XB are related to the photon and jet rapidities in XT in this manner, or in also you can relate it to the photon jet mass M and photon jet rapidity Y. Now, the reason this is interesting to keep in mind as we look at some of the data that you'll see shortly is that if the photon jet system is produced near y equals 0, then the relevant values of XA and XB are roughly m over us. And if the individual photon and jet rapidities are near 0, then the relevant values for the 2 momentum fractions, XA and XB, are on the order of XT. So you can look immediately at a plot of some data and realize what values of X you're going to be sensitive to. All right, so we'll start with some Tevatron data and look at both the photon jet invariant mass and the angular distributions. All bearing in mind what we're trying to do is to see if the photons are being produced in roughly the manner that we expect and with the angular distribution that we expect. So here's some D0 data from run 1. It is in fact the only data showing a photon jet mass that I'm able to find. And you'll see that it does in fact look to be in rather good agreement with the theory. So that doesn't tell you a lot about the detailed dynamics, but it does tell you that the photons are being produced at roughly the rate that one would expect. It's really a test of two things. It's a test of the PDFs involved, the particle distribution functions, and it's also a test of the overall magnitude of the partonic level cross sections. And it seems like, at least at this level, that test is passed successfully. Okay, photon jet angular distributions. QCD Compton and annihilation processes are both fermionic exchange, that is, quark is being exchanged in the processing, and the differential cross-section at the parton level behaves as 1 over 1 minus cosine theta spot, as cos theta star goes to 1. Contrast that to the standard quark-quark-quark-gluon and gluon-gluon processes, which all have components which correspond to gluon exchange. They behave as 1 minus cosine theta to the power minus 2. So jet production angular distributions are expected to be much steeper in the limit that cos theta goes to 1 than the direct photon subprocesses. Again, see the appendix where I've shown you how to derive those particular relations. Now, here's a comparison of data both from D0 and from CDF. And you'll notice that the results are in very nice agreement with the expectation on the theory, which is given in green here. On the right-hand plot, the CDF data show the angular distribution measured for dijets, that's in the purple, the photons in the red, and W plus 1 jet, and that's in black. And you'll notice that the agreement's pretty good in all of those cases. And in particular, the photons are being produced with a significantly shallower angular distribution than one would expect for the purely jet production case. So that's good. It says the angular distribution is what we would expect based on the just the lowest order diagrams, with a little bit of next to leading order correction thrown in. Now, just as an aside, those predictions were done using phase-space slicing method because there you're looking at a photon which has certain isolation cuts applied to it, which we'll talk about in a few minutes. And it's a photon and a jet in particular rapidity regions with particular cuts put on them. And in order to do that, you couldn't just go ahead and do the purely hadronic calculation because the Jacobian from the variables used by the experimentalists to the variables used at the parton level are exceedingly complex. And it was for this kind of calculation that a student and I first started doing the phase-space slicing calculations quite some time ago. Longer than I would like to mention. But that was the original motivation for developing that particular technique as discussed in the appendix, was to be able to look at angular correlations such as that. Okay, well, that's a measure of what goes on basically at the 2 to 2 level, with a little bit of next leading order thrown in. From those sets of data, the angular distribution and mass distribution, you get the idea that maybe the direct photons are being produced about the way we think they should be. But can we look closer? Yes, we can. You can look at 2 to 3 final states. What about photon plus 2 jets? In that case, there should be some very specific correlations between the jets and the photons. And this process has been measured by CDF. And here, this is going to take a little bit of explaining. First of all, you don't have to worry too much about the yellow. That's a background that's estimated based on a double scattering event, where you have a jet pair being produced and a photon being produced in the second hard scattering. And that gives a background to this, but you'll notice this is on a semi-log plot, so the yellow, although it appears large, is actually a small fraction of what's shown. Now, what's plotted here, first is the mass distribution of the photon in two jets. That looks good. The histogram, this theory agrees very nicely with the data. And then, the next three plots show you the energy fraction of the photon, that is the transverse energy of the photon as a ratio of the photon plus two jet mass, and for the same for the lead jet, same for the second jet. These are similar to the X1, 2, 3 that were discussed in Carlos' lecture. And what it is a way of showing you how the energy is distributed between the photon, the highest energy jet, and the second highest energy jet. And you notice that everything is in very nice agreement. So it looks as if the photons and jets are being produced pretty much as you'd expect. Of course, there's a caveat here. Two caveats. It's a semi-log plot. You can hide a lot with a logarithmic axis, and it's a leading order calculation. Just the tree level, 2 to 3 sub-processes were put in. Okay, here's another way to look at it. This is the photon ET distribution, highest energy jet ET distribution, and second jet ET distribution. Again, you see that these photons and jets are being produced at the level you'd expect and with the correlations that you'd expect. Okay. What other kinds of correlations can we look at? Well, I mentioned that one of the surprises that you would encounter as you dug into direct photon production was this fragmentation process. It certainly wasn't included as a part of the initial leading order sub-processes, and so people wanted to see if you could actually find evidence for fragmentation in the data. And one of the first experiments to look at this was UA2. And this plot, I have to apologize, is a little hard to make out. It's actually taken from a copy of the preprint that was online at CTEQ. Unfortunately, the data, this original data was published in nuclear physics, and we all know nuclear physics won't put their stuff online unless you have a subscription. So anyway, what this shows is the phi distribution of hadrons observed in either purely hadronic events, photon events, or W events. And here is the peak at 180 degrees. So we've got hadrons being observed in a jet here. And then on the opposite side, well, you've got a broader spread out region of hadrons that would, in the hadronic case, be the away side jet. The data points here are for direct photon production. And you'll notice they're right up here with the hadronic case on the away side where the jet occurs. On the trigger side, that's phi equals 0, where the photon occurs, there are a lot fewer hadrons. Not 0, but fewer. The solid line here indicates the level of hadronic energy in W events, and it's a measure of what would be coming just from the beam fragments. So what you see here is that the photons don't have as many hadrons on the same side as the photon is. They don't have as many as you would expect for a purely hadronic process, but they have a little more than you'd expect for minimum bias events. And so that's a way of saying that photons are often isolated, but not completely, that there is some level of fragmentation involved. So that's in accord with what we'd expect. Now, it's difficult, and I'll show you why, to put better constraints on the fraction coming from the fragmentation component, but at least this is consistent with the fragmentation component being. Now here's some data from CTEQ. And what you see here is the energy, transverse energy, inside a cone of radius 0.7. That radius is calculated in terms of a delta phi and a delta y about the direction of the cone. So radius of 0.7, about the photon. And you see three things here. Non-photon events, that is jet events, have a lot of energy in the cone. The minimum bias events, that is just ordinary events that don't have hard interactions, are going to have this dashed line. And the red and the green data points are two different ways of measuring direct photon events. And what you see here within the rather large errors is that the direct photon events end up having about as many hadrons around them as the minimum bias events. So you cannot say from this plot here that you can identify a fragmentation component. That's, I'll show you that that's not inconsistent with the expectations, but it does mean that it's going to be very difficult to look at associated energy with the photon in order to reconstruct some fragmentation component. Okay, so what I've shown you is that photons are produced with the expected angular distribution, which is flatter than for dijets. The photon-jet rapidity correlations are what you'd expect. Photon plus two jet events appear to behave pretty much as you expect. Photons are accompanied by fewer hadrons than purely hadronic triggers, but more than for the W events. And so basically, it looks like things are working pretty well. But we can go further. We can look at photon interactions now, putting the photon in the initial state. Basically, what you have to do is just do a little bit of crossing to go from the photon in the final state to the photon in the initial state. You can go through all of the same kinds of arguments that I went through before. What you'll find is that there are collinear singularities that are related to, say, a photon splitting into a massless quark-antiquark pair. And you can absorb those, factorize and absorb those into the photon part-time distribution. So you can actually calculate the distribution of a quark and a photon, a gluon and a photon. And if you'd like to know more about how that's done, check the lectures from the CTEQ 2001 Summer School. Those were devoted solely to photo production. So here are the cross versions that you would need if you were looking at three-jet final states. They're the same processes that we were looking at, just slightly rearranged. And again, one can look at three-jet production, and you have these same type of energy fractions. Now they're going to be the energies of the jet, not the transverse energy. And what you see from this plot is, in fact, that the three-jet mass in photo production behaves rather as expected. And the theory gives a good agreement there. Here you see the energy fraction. This is x3, this is x4. x3, 4, and 5 with this notation are the same as in the previous talk, x1, 2, 3. So there's no x5 plot here because x3 plus 4 plus 5 adds up to 2. You'll notice that, in fact, the histogram and the curves, the data and the curves are in good agreement here. The dotted curve is what you'd expect just from phase space, so you see some significant deviations from phase space that are nicely described by the QCD matrix elements. Likewise down here, that you can see some asymmetries in these plots. Those are real. They're the effects of cuts on the various angles between the jets, nicely reproduced by the theory. Okay. In the case of direct photon production, we saw that there was the direct component, or point blank, and the fragmentation component. The nomenclature that's used in photo production is that you have a direct piece where the photon interacts in a point-like way, but you also have a part that involves the photon PDF, and that's referred to as the resolved piece. Now, in jet photo production, in lowest order, you'll have two jets produced. You can measure their rapidities, you can measure their transverse energies. With that information, you can deduce the X that should have been representing the momentum fraction of the parton that came from the photon. In the point-like part, that would be 1. But for the resolved part, that would be less than 1. And so you can, just using the variables that you're measuring experimentally, you can break the data into two pieces, one that is mostly the direct piece, one that is mostly this resolved piece. The direct part, well, that should have an angular distribution for the dijet system that's 1 over 1 minus cos theta. That's analogous to the lowest order direct photon piece, whereas the typical boson exchange processes will give us a 1 over 1 minus cos theta squared for the resolved part. And indeed, this is observed in the data. You have to look closely because this scale only goes up to 6, this scale goes up to 12, this scale that fit on the same page. So they look the same, but in fact one is twice as steep as the other, and you see that it's in nice agreement with the theory. So the jets are produced with the same angular distribution that you'd expect. Now that was a nice test. Didn't have to rely on comparing to jet production, and you didn't have to rely on two different types of processes. You could slice the data and look at the resolved piece, you could look at the direct piece all at once, the same data set. Why can't you do that with direct photons? Why can't you slice the direct photon data into a fragmentation piece and a direct piece? Well, it's basic kinematics. In the case of photo production, you have photon PDF, you've got a proton PDF, you've got XA and XB, two pieces of information that you need to sort out, and you've got information from two jets in the final state. That gives you enough variables that you can solve for the X's of both the photon and the proton. So you know what the incoming momentum fractions were for the colliding particles. In the case of direct photon production, in the fragmentation events, you still have the two initial state X's, because you have two hadrons coming together, but you also have a fragmentation function in the final state. So you've got three variables. Not enough information to deduce what these three variables are. So that's the fundamental problem that for years has bedeviled attempts at trying to separate out the fragmentation or Bremskollen piece from the direct piece in photon production. Okay, so both the photo production and the direct photon data that I've shown you really support the two-component picture of the dynamics. There's a direct piece in each of the processes, jet photo production and in direct photon production. So the photon interacts in a point-like manner with the hard scattering subprocess. But in addition, there's a fragmentation type of piece or a resolved type of piece, depending on whether you're looking at photo production or direct photon production. They involve either photon distribution or photon fragmentation function, and you can calculate those, calculate the evolution of those with the Altrelli-Parisi equations. Everything seems to hang together. The fundamental interactions involved in producing photons or having photons interact in large momentum transfer processes seems fine. Every one of the tests that I proposed has been passed. So what's all the fuss about? Well, the one thing that's gotten the most attention over the years has been single photon inclusive cross-section. It is a very difficult thing to measure. It's actually not as hard a thing to calculate, at least you might think. Because what's happening here is that you're integrating over the partons, leaving the photon as being observed. It's a hard measurement to interpret because you've wiped out all the other clues as to what's going on with the dynamics. You're just left with the PT or possibly eta distribution to look at. Now, the fact that it's an inclusive calculation means that it's somewhat easier theoretically. You can do the integrations by either technique that I mentioned, either with phase-space slicing, or you can actually do them analytically. And so you can make predictions. But there seems to be a problem. And the problem stems ultimately from the fact that the PT spectrum is very steeply falling, especially at the lower energies or at the higher energies at lower PTs. So it's especially susceptible to any resolution smearing effects on the experimental side, and also to approximations that are made on the theoretical side. Okay, so there are a variety of programs that are out on the market. Some use analytic calculations, some are Monte Carlo based. It just depends on the observable you want to look at. We'll start here by looking at some Tevatron data. And let's see, we've got data from both CDF and B0. These are run 1 data taken at 1800 and 630. And you look here, gee, on a semi-log plot like this, everything looks great. And it confirms your expectation. Yeah, things are being produced about the way you'd expect. It looks like the energy dependence is right. Here it looks like the rapidity dependence is right. B0 has 2 different rapidity ranges here. So things are looking pretty good. But of course, you can always look on a linear scale. And then when you look on a linear scale, you notice, a bit of an excess here at the lower PTN. Looks like theory's a little high at the other end of the spectrum. You might say that there's a bit of a slope here that isn't accounted for by the theory. Here with D0, especially at the central region, which is the same region that CDF measured, you might say the same thing. All right, let's look a little closer at the 630 data. Here you see the 630 CDF data are blue, 1800 are red. Interesting. Looks like there's an excess here, at both energies. Toss in some UA2 data, and it looks like the same sort of behavior. It looks like the data have a steeper dependence in transverse momentum than the theory. Same thing here for D0 at 630. Looks like the rapidity dependence is about right, but the PD dependence is a bit more. So you say, well, what could possibly explain what's going on? And you might want to think a little bit about the fact that in order to measure photons at these collider experiments, they actually have to put cuts on the electromagnetic triggers so that they can distinguish the electromagnetic triggers from hadronic triggers. And these are referred to as isolated photons. They put specific kinds of isolation cuts on them. And, well, that's going to reduce the, or cut out events that have hadrons accompanying the photons nearby. So it's going to reduce the fragmentation component, which dominates at the low, well, is larger at the lower PTM than high PTM. So you say, gee, if you're making an error on the isolation cuts, then, well, maybe that's what the problem is. A typical isolation cut might be one that takes a cone of radius delta eta, delta phi. In this case, the cone is less than 0.4, and says that we'll only allow up to about a GeV of hadronic energy inside such a cone. Well, with the phase-space slicing programs, you can actually study the effect of that. It's pretty easy to do. For the 2 to 3 processes, you can just ask, is there any hadronic energy at cone about the photon? For the 2 to 2 parts, it's a little trickier. I've outlined what you do here. The reason is that at the 2 to 2 level, when you're dealing with fragmentation functions are really inclusive quantities. They've had the angular information of the associated hadrons integrated out. That's similar to you've actually seen that in the last lecture when we were integrating over x1 and x2 in order to get the total cross-section. That's akin to, well, doing the integral over the gluon transverse momentum is akin to doing what I'm mentioning here. The fragmentation component doesn't know anything about the radius, but nevertheless you can convert that isolation cut into a cut on the fragmentation variable z. And you'll notice that for a fixed value of this PT cut, say 1 GeV, as PT gets bigger, then this term goes to 0, z is pinched closer and closer to 1, and it just cuts down on the fragmentation contribution. That's shown here in a study by Kitani, Fontenot, Diag, and Coulomb. This is the fragmentation component with a PT cut of 2 GeV relative to the inclusive case. And you see that the fragmentation component is reduced as you go up in PT. Here's the total cross-section, and you see that it's running at about 80% of the fully inclusive cross-section. So what that tells you is that even if you threw away the isolation cuts, you totally remove them. In this case, you could only increase the cross-section by about 28%. If you look back at some of the data, you notice here that this is data minus theory over theory, and then going up to 100%. So this excess, or this excess, cannot be explained even if you were to totally remove the isolation cuts. So the fact that we're dealing with isolated photons in the collider energies is not the answer to what's going on. So here's that plot I showed you at the beginning of the talk. And what you see here are the collider data down at low values of xt. That's because PTs are running, say, from 20 up to 100, but RODOS is 1800. So they're low xt, which means you're probing low values of x in the part-time PDFs. Here are fixed target data, and of course they're at higher values of xt because RODOS is smaller. Okay. A couple of comments. When you plot the data versus xt, that tells you something, because it tells you what regions of the part-time momentum fractions are relevant. You might say, gee, I'm doing a terrible job with the PDFs, that's why I couldn't explain all of the data. But in fact, for data that are at the same values of xt, it's going to be very difficult to get the theory to give that much energy dependence, because you can't do it through the PDFs. Part-time distributions cannot explain differences at fixed xt, and we've already figured out that the angular distributions and sub-processes seem to be right, so what could be wrong? Well, one thing that could be wrong is that perhaps some of the data are inconsistent with each other. It's possible. But it would be appropriate to look at some other data sets and then to ask whether there are any theoretical ingredients that maybe we've left out. Now, here's a plot that shows some data from Phoenix at RIC. It's taken a RODOS of 200, which kind of fits right in between the collider regime and the fixed target regime, and you notice that the agreement is rather nice. So that's a good sign. Here's a fixed target experiment that was buried in that cluster of points on the right-hand side of those XT plots. This one's UA6, and I want to use this because I'm going to come back to it in a few minutes. This shows next to leading order predictions for the PP and P-bar PKs, and you notice that they're both a little low. Proton is lower than P-bar P is. the rapidity distributions are a little flatter than the data show. But if you take the difference, P bar P minus PP, you get very nice agreement. Now, I want you to hold that in your mind because we're going to come back and visit that shortly. But this is an interesting test here. This knocks out the annihilation piece. This knocks out the piece that involves an initial state gluon, leaves the annihilation piece, so it comes from P bar P. Seems to agree rather nicely. It's interesting. Okay, so what's going on? We see that the theory and data have different shapes. The various energies that we've looked at. Some of the lower energy experiments show the same kind of behavior. Some don't. Has that been seen anywhere else? And the answer is yes. This reference here, Orange, van Maasdijk, Giel, Berlin, actually compared what's going on in direct photons to what's going on in hadron production. And I'm not going to go through a detailed comparison, but I'll just point out that if you look at high zero production and you do a data over theory comparison, this band is between 2 and 3. That says the data are 2 to 3 times higher than the theory predictions down the fixed target rate. That's not a good thing. And yet, something strange happens. As you go up in energy, here's root S of 63, here's Phoenix at root S of 200, here's UA1 at 630. The agreement's great, even down to low values of transverse momentum. So, at least in the case of pion production, things look okay. So what's going on? We've got a situation where some of the fixed target direct photon experiments disagree with each other, presumably. There is, however, an excess of data over theory for all of the single hadron inclusive experiments of the fixed target regime. But the agreement between theory and experiment is very good by root S of 200. So you might conclude that you need an improved method of calculating the single particle inclusive cross sections, at least in the fixed target energy regime. And it turns out that there's a way to improve this situation. And it has to do with resummation. The idea is you've got a steeply falling spectrum, and that means that it's not energetically favorable for either a hadron or a photon to be produced in a fragmentation process where a lot of the energy goes into unobserved fragments. So the way of saying that the average value of Z for these fragmentation processes is going to be near 1. The fragmentation functions behave as 1 minus Z to the power. That's basically what's forcing Z to be near 1. Sorry, back off. Kinematics forces it to be near 1. The fact that it's steeply falling means that anything that you do that's going to change that Z dependence can strongly affect the answer. So, what's the basic idea behind threshold resummation? In inclusive calculations, you've seen the collinear singularities, but there are also singularities related to soft gluon emission. In the last talk, that would be the case where both x1 and x2 went to 1, forcing x3 to go to 0, the gluon emission. Well, there's a singularity there. You saw how that worked in the last talk. The fact that the fragmentation variable is forced to be near 1 means there's not a lot of phase space for gluons to be emitted. So, yeah, the singularity that exists exactly at the end point of Z equal 1 will still cancel appropriately with the corresponding singularities in the virtual diagrams. But there can be large logarithmic remainders that are coming about from these soft gluons. And the classic example of this is E plus and minus goes to jets, looking at what's called a thrust distribution George Sturman is going to be talking about such resummation later on in the school. Just to point out, if you were doing a 2-to-2 calculation, and you look up these Mandelstam variables in the appendix, you would have S and T and U, S corresponding to the center of mass energy of the parton system, and U and T are angular variables, but S plus T plus U adds up to 0. In terms of this variable W, which goes along with the variable V, which was mentioned in the phase space, for the few phase space in this talk, the soft gluon singularities occur at W equals 1. And there are terms that are of the form log n of 1 minus W divided by 1 minus W. And it's those large logarithmic corrections which need to be resummed. They're going to be important anytime the gluon emission phase space is reduced by the kinematics of the process. So in a recent paper by DeFlorian and Vogelzang, they applied this to the case of pi-zero production. And remember now, pi-zero production, we're going to have at fixed target energies the two initial PDFs with large x, a fragmentation function with large z, and it turns out that these resummation effects are huge. And so here are some examples. The NLL curves have the resummation included. NLO curves do not, and you see that there's a big increase here at root S of 23, here at root S of 32. Also, if you look closely, the bands corresponding to different scale choices are closer together when the resummation effects are included. So here's an answer, maybe an answer, to what went wrong with pi-zeros. Now, if you go up in energy, an interesting thing happens. The fragmentation variable is not pinched at high values of z anymore. The resummation effects are less important, and hence the enhancement that you get is much reduced. Well, that's good because you already agreed with the data up at the Rick energy regime and higher. So resummation, in this case, fixes the fixed target disagreement and leaves the higher energies alone. So what about direct photons? Well, there are two pieces there. You can apply it to the point-like, you can apply it to the fragmentation part. Nick Hidnakis and I looked at the point-like part some time ago, found that the increase was actually rather minimal. The band narrowed, but the actual cross-section itself was not significantly increased. DeFlorian and Vogelzang have explored what happens to the fragmentation part using the same formalism that they used for the pi-zeros, and there an interesting thing happened. Here's the next to leading order level of fragmentation and the level of the direct piece that you expect. This is just a fraction of the cross-section versus PT. When they turned on their resummation, the fragmentation piece went way up, and hence the corresponding amount of the direct part went down. So the fragmentation is contributing a lot more than you might have expected. Here's another way of plotting it. This is a K factor, and you see that it's actually getting to be quite large at large PT, going up to 2.5 or even 3. And so it gives you a significant increase, not enough to describe all of the data points in this particular plot, which was from 706. Here's, however, a plot of the UA6 data, the proton-proton data, which, as you'll recall, had the theory underestimating the data. Now it looks like the theory and the data agree rather nicely. Again, if you go up to the ISR energy range, the agreement is still good because the fragmentation contribution is decreasing. Now, the interesting thing about the UA6 data that I said, remember that the difference in the P-bar-P and PP cross-sections was already well described. But in the difference, the fragmentation piece cancels out. So the enhancement that's due to this resummation doesn't affect the good agreement that was already there, but it does bring in the, especially the PP data, into much better. So bottom line on resummation, You get reduced scale dependence, you get an enhancement in the fixed target regime, but the effect is smaller at higher energies. It can improve the agreement with some fixed target experiments. And there's an additional effect that I don't have time to talk about this year, but which I did talk about last year, and that's joint resummation that includes some part-time recoil or KT effects in a self-consistent way with the threshold resummation that I have talked about. And you can see that in the talk I gave last year, which is on the web. Okay, so there's an interesting review. I've cited it here, came out this year. It shows, here's a comparison with some recent D0 data. It looks to be quite good. These are different results for different choices of scale. Caveat here, the data cut off at 25 GeV in PT, which is right where the excess started to be seen in the previous data sets. There's the Phoenix data, agreement is good. Here's a compilation that shows collider data, the new D0 data. Here's the Phoenix data. The agreement looks to be good. Here's the fixed target range where, again, I've pointed out that one really needs to include resummation effects to make this plot look better. And now I'll just conclude with a couple of amusing comparisons. Here is, let's see, there's CDF of 1.8, and plotted here with the systematic errors added in quadrature with the statistical errors, and the authors claim that they say, well, within the errors there is no excess at low PT. Same thing over here with UA2, CDF, and D0. Again, the systematic errors added in quadrature with the statistic. Then you'd say, huh, is there a significant slope here, or is everything fine? Within the errors shown, everything looks good. But it's often, in the way you plot things, here's the same, a selection of the same data plotted without the systematic errors, and here plotted with it. And you'd say, gee, within the errors there's no significant slope. Here you'd say, looks like it's a bit of a problem. So you have to ask yourself, should you be adding the systematic and statistical errors in quadrature? Well, not really. If they're correlated systematic errors, and you just add them in quadrature like this, you're going to overstate the true error. These correlated systematic errors are the ones that allow the data to be shifted up or down uniformly. Whereas when you add them in quadrature like this, it makes them look like each data point is statistically independent. So it's a bit of a misleading thing to do, to add the systematic and statistical errors in quadrature. Now there's another point that I would like to make. Thank Steve Pullman for emphasizing this to me. Here's a plot that I showed earlier that shows CDF at 630 and 1800 versus PT. And you see this excess. And here it is versus XT. Remember, when you plot versus XT, it says these guys are being probed at the same value of the parton X. So there's some physics that's missing here because there's no way that I can get this with a next to leading order calculation. I cannot simultaneously describe the blue and the red data points. Now, in the Orange et al. Review, they said the errors are large. It doesn't matter. The theory is doing well enough. But if you really dig into it, maybe it's not quite well enough, and there's a little bit more work that has to be done. So I would simply say there's still room for theoretical improvement. For example, resummation in describing the PT distribution. We haven't got it all right yet. This is a nice plot, nevertheless. It does show, this is from the review paper that the Washington Company did. It does show there's very nice agreement, for the most part, in direct photon production, covering 9 orders of magnitude. So here are the summary and conclusions. What I've tried to show you is that the dynamics of photons interacting in high PT processes I believe is well understood in general. We've got a good picture where the sub-processes seem to behave as they should, the PDFs behave as they should. There's broad agreement, with some caveats, over a wide energy range. There are theoretical techniques that need to be applied systematically over the full energy range. The resummation has been shown to make a difference in the fixed target regime. The recoil KT effects can be included using joint resummation. And so my parting words were, as I've shown here, we've got good agreement over 9 orders of magnitude, reasonably good agreement, although there are still some regions where detailed description requires, for instance.